Okay, hi. I'm James, and I worked with an awesome team, and we built this cool thing. And the project started last fall, kind of built it in the winter and this quarter. So Professor Virginia Desaw in the room is awesome. She was one of my advisors as well, trying casting, and David Medine. We worked with Roger Jennings, Danny, and Howard. So what is multi-touch? Multi-touch refers to the ability to have a surface sense your touch. So we could have this table could be a multi-touch table, provided it was able to sense my hands interacting with it. This table is a multi-touch table. You may be familiar with other things like iPad, or some other research in this area, or even in the movie The Avengers, they have these transparent interactive touchscreens, which are really cool. Now, there are all different types of technologies related to multi-touch, like resistive screens, capacitive screens, embedded in-cell screens. I'm just going to read them. Acoustic, infrared, optical, and vision-based screens. So many different types of screens. Well, the question is why? Why are we building all these screens? And I'll address that in a minute. So why research multi-touch? Well, very clearly on this data that I made up, we have LCD screens cost, this is costing thousands of dollars, is pretty much linear. So the cost to manufacture LCD screens, you do really tiny screens to really big screens, it's linear in its cost to manufacturers. But for touch screens, it's exponential, which they're almost, which is bad. Because our whole thing is, what if touch screens cost the same as LCD screens? What if we brought the cost down? What if we closed that gap? And if we close that gap, does that mean that all screens that we have can be touch capable? Because why not? The markets are entertainment, infotainment, retail, education, government, corporate, public space applications. Basically, these things can be everywhere. You can put them on your walls, the whole room, the ceiling, the floors, the tables, everything can be touch interactive. Question is, why not? Well, it costs a lot of money. Bring the cost down. So, what did we do? We built this multi-input sensing table. Yes. And why is it called multi-input? I thought it was multi-touch. It's multi-input because it has three different types of sensors. We have a camera, which is optical-based. It looks up from the inside of there up to the screen, and it uses an infrared setup, frustrated total internal reflection. So when I touch the surface of the screen, actually, I'll show you in a second, or after this presentation. When I touch, the camera sees my fingers as blobs. We also have pressure sensors, which are located in the corners of the screen. So this sheet of acrylic on the screen is resting on these pressure sensors, FlexiForce pressure sensors. They're rated at 0 to 25 pounds. And you can distribute your load differently on this surface, although it is a uniform sheet. So ideally, you wouldn't see, or in theory, you wouldn't see that difference, but you do. And then we have these acoustic piezoelectric sensors, which are these sensors that are able to detect sound. So when you hit a surface, a sound wave propagates throughout that surface, and it's the same thing with the sheet of acrylic. So we have our pressure sensors and our acoustic sensors going through an external sound card, and then it's processed using pure data on our Windows 7 PC, and the camera is going through Community Core Vision. These two send out information to our application, which in our case is a drumming app. So we can drum on the surface, and I'll explain why we made a drumming app. So what was the motivation behind this table? Well, human beings have our 5 senses and the 5 other ones we don't talk about, but we have 5 senses. We can see things, hear things, smell things, taste things, and feel things, in addition to being able to sense heat, cold, pain, motion, balance. So I saw that humans have all these senses. Why don't computers have these senses? So why multi-input? Well, in a lot of other setups, what they have is they have one type of sensor. So there's optical-based systems with one camera pointed up. If the camera goes on the fritz, it's game over. If your sensor dies, it's game over. If you have an acoustic-based screen with microphones around the bezel of the screen, and you have these different microphones, and some of them die, you lose your ability to do your touch detection. It's the same thing with pressure-based screens. If you have a resistive screen where you have 2 plates of wires that contact each other, if some of those wires lose their ability to carry a charge, you will have dead spots on your touch screen. So in a sense, the whole idea was, well, can we build in this redundancy? If we have a camera and some piezo's and some pressure sensors, Well, you make it so that if something on the screen breaks, the screen will still work, or the touch screen will still work. So make it redundant, kind of like humans. I don't know. In theory, the three sensors complement each other and improve the table usage. So that was the idea, was that if you add more sensors, the table will perform better. So here's our comparison matrix of the three types of sensors. So we have our optical, which is camera-based, our acoustic, which is the piezo pickups for sound detection, and then our pressure sensors, which determine force. So, speed. The camera's operating at about 60 frames a second, 60 hertz. But after all the processing, it drops down to about 13 frames a second. Our acoustic and our pressure sensors, however, are operating at 44.1 kilohertz, which is pretty fast. It's a lot faster than human beings have the ability to sense, I guess, our sensors. So obviously it's a clear win for the acoustic and the pressure sensors on speed. Quality, on the other hand, optical wins. The camera is a very good device for seeing the entire landscape, whereas the acoustic and the pressure are low quality. And I don't want to put this analogy out there, but if you close your eyes, it's a lot harder to, I don't know, interact, and you need a lot of training, but the brain will adapt. The computer, on the other hand, is out of luck. It's very difficult for the computer to just use the pressure and acoustic sensors for input location, although, and especially for multi-touch. And, yeah. Onset detection. Acoustic and pressure sensors are pretty much instant, as determined by the speed, with opticals delayed. But the XY accuracy, the camera is the best. It can determine where you're located. Now, there are schemes for developing XY accuracy for acoustic screens. There are these acoustic-based touch screens, like surface wave acoustic. And they work, but they're mostly single input, not multi-input. Same thing with force, pressure sensor, multi-touch, optical is best. They do poorly. Single touch, optical is pretty good, acoustic's pretty good, and static measurement, optical is best. Now, what's this multi-user thing? Well, all three of these methods aren't good for multiple people. So if you have me trying to interact with one portion of the screen, and you trying to interact with another portion of the screen, the computer, if it doesn't know who's who in this setup, won't know, you might be trying to control something and it might mess up. And we have some kind of workarounds for that, but there are cases where you can break the system. So here's the optical setup. We have our camera going into CCV, sends out TUIO messages. It's an MV Firefly capturing 60 frames a second, 640 by 480 resolution. It has an infrared bandpass filter on it at 850 nanometers. We have 850 nanometers, 128 of them shining into this sheet of surface acrylic. And when the camera lifts up, it sees the image of the infrared LEDs and some blobs. It's a very small image, I'll show you in a second, or after this presentation, what I'm talking about. We use CCV, and you get information like absolute XY positioning, blob size, intensity, and so on. The acoustic and the pressure sensors, they take in information, it's plugged into PD, pure data, which looks like that, it's visual programming. And we're using the piezos and the pressure sensors to plug in via quarter-inch jacks into this external sound card. The software is PD, sends out UDP packets to Kitty, which is what we're using for our application. So what was the cost of this project? We had approximately $2,500 worth of expenses, but fortunately, almost $2,000 of that was donated. The big ticket items were the computer, the sound card, the camera, and the LCD screen, as well as the power supply. Everything else, I had to go to Home Depot and other various stores and pick up, purchase, and assemble to what you see here. And we probably had over 1,000 hours of teamwork / I had a lot of time invested in this project, and it turned out pretty cool. So how do you build one of these awesome fun tables? Well, you take apart an LCD screen, you buy some sort of cabinet structure and add some aluminum. You put the thing on top with some acrylic, and then you cover it all up, and you get something similar to that. You also have to put a camera down below, as well as some backlights, or else you won't be able to see the screen. And then you add the sensors. Now, we built it in C-Lab, which is in the CSE building, and this is our setup. We kind of had to flip the table up and down a bunch of times. Ended up looking like that for a bit, and we had an awesome team consisting of Roger, Danny, David, Alric, and myself. the conclusion. Now, don't be worried, because like you're like, oh, this is a 6-minute presentation. What's going on? It's mostly a demo because the thing's cool, and I want you guys to see what's going on. So the conclusion: the multi-input sensing table provides both accurate temporal and spatial sensing resolution. So other tables only will give you accurate spatial sensing. So that's a camera-based system; it knows where your fingers are. But the temporal resolution is pretty low. In our case, we do both. And unlike other tables, our table uses more than just one type of sensor. So instead of just using one camera, we have the camera, 4 piezos, and 4 pressure sensors. So we will hold off on the questions while I do the demo, which I'm going to just walk over here. So basically what we have going on is, here is, oh, got to turn these on. Gotta give him a second. Oh no, live demo. What's going on? Close that. Reopen it. No. Well, just to.
Nope.
Hey, oh, it's my hand. Okay. So these lights have to warm up, which I forgot to turn it on right before I turned the computer on. But in any case, we have our trusty infrared LED pen, which will make this all extremely inaccurate. So here is the tracking of the pen. It moves around. Very cool. Now on this calibration screen, you can see this guy going on. So when you track, you get something like that. You move the pen around. The idea is you're supposed to be able to do that with your hand, but I have to let these things warm up for a second. Otherwise, they're not going to show. That was my fault. And all of you will be able to play with this after the presentation and throughout the day. So I can show you the sensors, the audio sensors. So here is our audio fire external sound card. And basically, this is what we take and then process in pure data. So right now, the first 4 channels on the left, these guys, are our piezo pickups, and then these 4 channels are our pressure sensors. So we have them ordered with the top left of the screen is 1, top right is 2, bottom right is 3, and the bottom left is 4. So if I hit this at 1, you start to see that they all pop, which is why we have to threshold them in such a way that we get them to accurately classify which one was hit. Because the sound wave is traveling out from wherever I hit, and it will hit all 4 of the sensors. And the amplitude is determined by how well the sensor is coupled to the surface of the screen. So I hit the first one, they all pop. Hit the second one pops more than the rest, the third, and the fourth. Now for the pressure sensors, the top left is channel number 5. You can see that that's going the best. Top right, that's going the best. Next one's going up, and this one's going up. So let's hope that after that brief interlude of discussing sensors, that the CCD stuff works. Almost there. Just gonna crank this stuff up. So you turn up the amp. Oh, there we go. Beautiful. Ish. So the next thing I can show you is pure data. So this is the pure data interface. Basically, this is what we use to process the sensors. So we have all of our channels coming in, and then we can threshold them at different values to determine what velocity, for the minimum velocity of the attack. It doesn't look that great, but this value is 4, this value is supposed to be 6. This was predetermined in calibration. This one is about 10, and this one's about 8. Good enough. And then we have this cool application, which I guess I'll show right now. Barring, let's hope it works. the application is called BAP. It is a drum pad application, and I hope everything works. All right, so this is the interface. And I might have to turn the sound up. Hey, it works. Okay, so the TUIO is still warming up, or the FTIR, the infrared, is still warming up. But basically what's going on here is I have the ability to interact with this drum pad using the pressure sensors and TUIO. So this is the piezo drum kit. So if I hit with the drumstick, the camera's not picking this up. If I hit with the drumstick, the different pads send out information. Now, you do see that it's misfiring, which is bad, but in our case, it's acceptable because everything is wonky, because I had to roll this over from the CSE building to here, and everything fell apart. It was quite sad, and I cried a little bit. Hey, the TUIO is working. So this is the piezo pressure drum kit. So this one will take in information from the piezos and the pressure sensors. So if I hit it softly, yeah, there. If I hit it softly, it's very soft. If I hit it hard, it's louder. So the whole idea with this one, although it's misfiring, but the whole idea with this one is that you can use the pressure information to determine the intensity of the sound of the drum. So this isn't doing anything optically right now. This isn't taking any information from the camera. I'm just hitting the table relatively close to those drum pad areas, and it's trying to take that information, and with the audio information, it'll determine where the hit occurs. With the pressure information, it'll determine how loud to put out the sound of the hit. And other tables can't do that. That's something cool. We have this TUIO drum, which works. Uh-oh, it just crashed. Well, that happens. I'll keep running it because no other option other than show you what I'm doing. Look at this. Hey, that's a kind of better track-ish. Maybe if I amplify it. Send video. Piezo pressure piano. Okay, so this guy has pressure sensors and the acoustic sensors. Oh. That's kind of funny how it bugs out like that, but hey, it works. The whole idea with this one was to show that you can hit it and play the piano. Yes. And it takes 5 seconds for each time you run one of these things to disappear. You may be wondering what's going on with this area. So if I could only drag this, I wish I could. I'm supposed to be able to drag this over. No, I'll just delete it. The whole idea is that you can try and make a very difficult composition by creating a sound element and then dragging it to the right to have it play on loop while you start taking other sounds and adding them in. So we have a demo video of that, which I guess I could show because it's the only thing that appears to be working. And we'll do that. And then later you guys can try and play with this and look at what it does. And then I'll end with this demo video and then I'll take questions. Demo videos on this flash drive. I feel like I'm juggling. I don't know how to juggle.
Some things are pretty impressive even when they don't have a full.
So, for those of you close, I guess you'll hear some of the sound. For those of you further away, I'll just talk over it. basically, the table has 128 infrared LEDs, the 4 flexi-force pressure sensors, and 4 piezo sensors on the corners. And then here is the infrared, the blob detection working wonderfully. You just have to leave them on, they get hot, and then they work great. There's 2 power supplies in this setup. One is controlling the light bars, there's 2 light bars. And then the other one is controlling the audio piezos. So, So yeah, this is it working in an ideal setting. There's also this oscillator, which I didn't show, but would have been very difficult to work with, given that it's not detecting my touch inputs. So in this case, I guess the table would be blind, but and then it's partially deaf and partially can't feel things. Well, it's partially blind. It's just old. I don't know. But it's not responding how I want it to, so we'll have to tweak that a little bit over the breaks and stuff. Because it did speak. You saw that. It kind of worked. And then we also have this soundboard, which some of you will want to play with. It's a Daft Punk soundboard. So you can play the whole Daft Punk song if you remember it. Oh yeah, and then we have these gestures to drag and move the sound elements around. You can play with those. And that's basically the project. So I guess now we can do questions.
Yeah, so at the beginning, you mentioned the idea of, really bringing the cost down for larger size touchscreens. Yeah. And I was just wondering how economical you think, the building in redundancy might really be.
Well, that's a great question. So the piezo sensors are about $3 each. So you can do anything you want with these guys. And the circuits for them will probably tack on another $4. So it's very simple circuits, and you can plug them into just about anything. So any cheap sound card you get, maybe a $25 sound card, and you have piezos that are detecting sound on sets. They're basically, piezos are like microphone buzzers, the little beeps. They're just discs that will, if given a voltage, will emit a sound, and they will also sense vibrations and turn those into it. The pressure sensors, on the other hand, after looking around at all the different types, we settled on these flexi-force pressure sensors, which are about $20 each. But they do have cheaper pressure sensors, but we wanted these ones because we thought the quality would be the best. And given that they were going to be in this kind of extended use where a load is applied continuously, the surface of the screen is applied continuously, we wanted to use those as opposed to cheaper ones which might just wear and tear. So the sensors themselves are relatively inexpensive. The bulk of it, though, is the cost of this external sound card, which you don't necessarily need to use. It's a very fancy piece of audio processing equipment for professional audio. And that was just something that we had laying around.
So how much was, the other day you actually said how much the whole thing cost. So how much did it cost just to put this thing together?
$2,500 is the sticker price. Well, there's no sticker price. I can't sell it because it's not mine in a sense, because some of it's borrowed. But the CSE department covered about $500 of that in terms of the materials that we couldn't get donated or borrowed. The TV itself was donated. And overall, I mean, with these projects, you just kind of get what you can.
But it's a hell of a lot cheaper, even at that price, than what it
would
would cost if you had it in these.
Yeah, a 32-inch screen would probably be about $8,000, $10,000. I mean, you normally get, well, it depends. Like the Microsoft Surface is about that price, depending on if you're research or if you're personal. Yeah.
Yeah, I was curious. So I've seen a lot of different experiments that do with sort of multiple-person, multi-touch interaction stuff, and I was curious if you're considering kind of like
Yeah.
That and what you get more out of it.
Yeah. So I mean the multi-user is definitely a different avenue. And in the beginning, the idea was, well, because I'm working with Professor Assad with this machine learning, and we had all these big ideas, but it ended up coming down to the implementation level, which is where at least it got built and it works, kind of. But with the machine learning aspect, the idea was, can we use these cheap sensors to then maybe build a sound profile for a user so that we know who's hitting it with their fingers, or can we use this other information to kind of build identities, and then from those identities classify who's using it. So, and there's and other people have done stuff similar, but security ideas where if it's not your table, and if it's not your table but you use it, you're not allowed to use it, you get locked out because you don't have the sound profile at once. I mean, stuff like that was, in the original planning of this, was thought of and talked about, but I mean, there's like how much soldering I had to do to put this thing together. Like these lights, there's 21 of these LED backlights, each of which has 2 wires going in and out of it, which is 4 solder joints basically, times 21, times the other LED light bars, times all of this. It's a lot of work. So.
James,
Yeah.
right there.
Thank you. Okay.